Okay, so I'm going to start kind of where I left off last time. So last class I was introducing us to this concept and the basic premise behind NMR spectroscopy. Specifically, we were dealing with Proton Nmr, so H1 NMR. And again, the whole idea behind NMR, or nuclear magnetic resonance, is the fact that proton nuclei have a net magnetic moment, right? And so if you take a proton nuclei in a molecule and you apply an external magnetic field, that nuclei can adopt either one of two possible outcomes or possible spin states, right? That nuclei can align with the field, right? And we call that the alpha spin state. And that nuclei can align against the field, and we call that the beta spin state. So we kind of consider it like little bar magnets. You can either align north or you can align south. And those two different possibilities or those two different outcomes actually do have a difference in energy between them, right? So the basic idea behind NMR spectroscopy is that we take a molecule, it's got hydrogen nuclei, we apply an external magnetic field, those two different spin states are populated, right? And then we shine in light of different radio frequencies that has an energy that's equal to the difference between these two possible spin states, right? And so when the energy of the light that we shine in has that energy difference, then we will see resonance, we'll see absorbance, and that's what we're actually measuring in our overall NMR spectrum, okay? Now, there's a couple of different things that we took away from this, right? So number one, the thing that affects this energy difference, right? The thing that affects the frequency of light at which our molecules are going to absorb overall is the strength of this external magnetic field, right? Or the strength that is felt by this external magnetic field. So overall, the larger the magnetic field, so the larger our magnetic field, the larger the overall energy difference, the larger the delta E for the alpha and beta spin states, the higher frequency we're actually going to see absorbance. The higher frequency of light, we're going to see absorbance. And remember, there is a direct proportionality between energy and frequency when it comes to light. Okay, so then the question was, well, what type of things affect this magnetic field, right? So if we just have a set magnetic field that can be like, I forget, like 14 Tesla, I think, is a common magnet that they use. What other things are going to affect the magnetic field that these protons feel, right? These nuclei feel in the overall compound, right? So we talked about how, well, okay, if we talk about something like methane, right? And again, in methane, we're looking, in terms of our NMR, we're looking at the nuclei of these guys, right? And we're saying, well, what other parts of methane are going to affect the magnetic field that is felt by these nuclei, right? And so then we pointed out, well, okay, in methane, what is in this bond, right? So what is in this bond specifically is electrons, right? So we've got electrons that populate these bonds that are near these nuclei, right? And electrons have their own little magnetic moment as well, right? So we talked about spin quantum number is essentially the manifestation of that magnetic moment. And so because of that, because these guys are spinning charged particles, the minute you apply an external magnetic field, they're going to begin to circulate in a way that opposes that external magnetic field, right? So the more electrons that are in these bonds, right, or near these nuclei, the more opposition those nuclei are going to feel for that external magnetic field. So overall, because of that, we feel less of a magnet, or less of an external magnetic field because of that, right? And so because we feel less of a magnet, because we feel less of a field there, we're going to have a smaller energy difference. We're going to absorb light at a lower frequency, right? So this thing overall was something called shielding. And so the more electron density around those nuclei, the more shielded they were, the lower the frequency of energy, or the lower the frequency of light that we're actually going to see absorbance. Okay, so then we compared that to something like trifluoromethane, right? And again, with respect to NMR, everything we do is still looking at the nuclei of hydrogen. We're not looking at carbon necessarily until we get to the end. We're not looking at fluorine, again, necessarily until we get to the end. But for H1 NMR, we're looking at hydrogen. We're looking at hydrogen nuclei, right? So now the big difference here for this guy, comparatively, is the fact that carbon, which is attached to this hydrogen that we're looking at, and we're looking at the electron density around it, this carbon is attached to all these really electronegative groups, right? Fluorine is the most electronegative element on the periodic table. So they're very, essentially what we call electron withdrawing. And this is what we mean by inductive effects overall, right? These guys tend to withdraw all this electron density away in these bonds, right? So these guys withdraw all this electron density, which leaves this partial positive on carbon. But most importantly, that causes carbon to withdraw electron density in this bond, right? So this movement or this withdrawing of electron density essentially leads to the fact that there are less electrons around our hydrogen nuclei, right? And so because there are less electrons, there's less of this overall shielding effect, right? So because of that, this guy has a larger energy difference. It feels a larger magnetic field, right? Because again, we're applying this constant external magnetic field, but because these electrons are not opposing it as much, it does feel a larger energy difference, a larger magnetic field overall, and so this guy will absorb at a higher frequency of light compared to these guys, because they are shielded, right? So because these electron withdrawing groups withdraw this electron density, we call this overall deshielding. So if electrons are nearby, because there are electron donating groups or not any electron withdrawing groups, we call that shielding. Whereas if there are electron withdrawing groups removing that electron density, we call that overall effect deshielding. Okay, and so then we talked about a couple other things. So that was the basics, right? And so we're going to get into this idea behind shielding and how that affects the signals in our NMR spectrum as we move through today. We did talk about how to know how many signals you're going to get, right? So again, chemically equivalent protons will give rise to the same signal, right? It's only chemically non-equivalent protons that'll give rise to different signals. We talked about how you could know whether or not something was chemically equivalent or not. And then we started talking about how we actually took spectrums, right? So if we have a molecule and we're interested in taking the NMR spectrum, we always insert an internal standard, right? And so that internal standard is something called TMS. It stands for tetramethylsilane. The protons that are in tetramethylsilane are like the most shielded protons of all. So because of that, in our NMR spectrum, these protons will absorb at the lowest frequency, the lowest energy. And they essentially set what we define as our zero in the overall NMR spectrum. So in every NMR spectrum, you have your compound, but you also have TMS in there to define your zero on your overall spectrum. Right, so again, with respect to NMR, we're measuring an absorbance, so this is going to show up as a peak. And so we're going to talk about what these various peaks mean, right? So for right now, we're just going to focus on the number of them. So for example, right here, we've got a peak, we've got a peak, we've got a peak, a peak, a peak. The number of them, number one, is going to give the actual number of chemically non-equivalent protons. And then where they're at is going to tell us a lot about the electron withdrawing groups that are nearby overall, that are essentially shifting where you would expect to find their signal due to that deshielding effect overall. Okay, so just note, we also define what chemical shift stood for. So the reason or the whole rationale behind why we talk about chemical shift dealt with the fact that depending on the NMR spectrometer that we actually use, depending on the strength of the magnet, depending on the operating frequency of the instrument, was going to depend on where we actually measured these frequencies, right? And so to kind of normalize that so that we could get the same value regardless of the type of spectrophotometer or spectrometer that we were using, we defined everything relative to chemical shift, right? So chemical shift was the frequency at which a signal absorbed relative to TMS, right, divided by the operating frequency of the instrument multiplied by 10 to the 6. That's why we have the part per million. And so now, no matter what, if we have a compound we measure in a 300 megahertz instrument, we're going to get the exact same chemical shift if we measured it in an 800 megahertz instrument. It doesn't matter overall the operating frequency of the instrument. Okay, so again, just as a reminder, going from 0, which is our most shielded protons, our internal standard TMS, as we move from right to left, so I'll call this right over here, we're going left over here. What we're finding is we're increasing overall the frequency. So right to left, we're seeing an increase in frequency with respect to the light that we're actually shining in. If we're getting signals, that's also leading to an increase in energy, right? Because remember, the larger the frequency, the larger the energy difference between alpha and beta. And what that's telling us in terms of what's nearby to influence that, what we're increasing overall is the deshielding, right? So we're increasing what we're going to call electron withdrawing groups, or we're increasing the overall inductive effect. Okay, so now we're going to go through a couple of just basic numbers about where you could expect to see protons overall, and then we're going to allow you guys to kind of attempt to predict where you would expect to see certain protons in the NMR spectrum, okay? Okay, so again, we've been referencing this deshielding, and this deshielding is due to, again, what we call inductive effects or electron withdrawing groups. So overall, what we find is the more inductive effects or the more electron withdrawing groups are near our protons, the overall increase we'll find in deshielding, the overall increase we'll find in the chemical shift, okay? So for example, if we took the protons of methane, right? So again, in NMR, we're looking at protons. So these guys are all chemically equivalent, so we would only expect to find one signal for this molecule, right? We could give you kind of just a round off estimate about where we'd expect to find these, and we would expect to find them about 1 part per million relative to TMS. So methane, those protons are just going to give rise to one signal. And if we had our TMS here, then we could expect to find these guys. If this is 0, then this would be at about 1 part per million. Okay, so now let's compare that with this monoiodide methane, right? So we've replaced one of these protons with an iodine, right? Again, what we're looking at here is the signal that we'd expect for these 3 protons. So these 3 protons are chemically equivalent. They're again going to only give rise to one signal. But now comparatively, where we would expect to find these guys is 2.2 parts per million, right? So again, the only thing that's changed, we have one signal, we have 3 protons that are chemically equivalent. The only thing that's changed is the fact that we have now an iodine directly attached to that carbon that those protons are attached to, right? And again, iodine is fairly electronegative. It's not super electronegative, but it is electronegative relatively. Hold on. Okay, so that was a fire alarm. But I'm back, and so, okay, so what we were saying, yes, so normally you'd see methane's protons show up at about 1 part per million. If we add a semi-electronegative group like iodine to it, then that shifts it farther, what we call downfield, right? So to a higher parts per million, which is 2 parts per million. Again, as we increase the electronegativity of that group that's nearby the protons that are giving rise to this signal, we continue to see a shift farther downfield to higher parts per million, okay? Okay, so overall, the more electronegative the group attached, or the more electronegative the group that is nearby, the greater the chemical shift that we see, right? So we'll see the protons come into resonance at a higher chemical shift. This effect is also additive, right? So for example, if we had protons that were nearby a chlorine, we would expect to see those protons at 3.1 parts per million. If they're nearby 2 chlorines, though, we're going to see an increase in that. So this is 5.3 parts per million. And if they're in nearby 3 chlorines, then we're going to see an even greater increase. That's at 7.3 parts per million. Now, this chlorine, fluorine, bromine, all of these guys, this is just trying to illustrate to you what an electron withdrawing group or what an electronegative group does to the chemical shifts of protons, right? I don't expect you guys to memorize these numbers, but I will tell you when I do expect you to memorize a number, okay? Okay, and so then one other thing to note too, so it's nice when we draw all of these nice Lewis structures out here, so you can see the carbons, you can see the protons, but note that frequently we're going to be using bond line structures. So for example, when we had a bond line structure, something like this, the kind of, I guess what I would really stress is that you understand bond line structures, because when we're dealing with NMR spectroscopy, we're looking at protons and they are explicitly not drawn in bond line structures. So just be careful and make sure you know when you're looking at a bond line structure how many protons are attached and what other things are attached to the center that you're interested in, right? So for example, let's say that we had a molecule like this where I've drawn the bond line structure. Again, this guy is a carbon, all right? So we have any of our vertices, any of our endpoints are all carbons. This carbon is attached to a chlorine, which is a nice electronegative group, but we know that it's attached to a chlorine, it's attached to a carbon, it has to be attached to 4 things, so we know that there are 2 protons here, and it's important to note that these protons are chemically equivalent, so we can call these protons A, or more importantly, what I'm trying to refer to is as protons alpha, okay? So we've been talking about the inductive effects having the presence of this electronegative atom and how that affects the chemical shifts of the protons nearby. It is important to note now, though, that effect, that deshielding effect, it tapers off with distance, right? So again, this is a bond between our carbon here and our chlorine. Because this carbon is directly attached to this chlorine, we call this the alpha carbon. And then these hydrogen down here are what we would call like alpha hydrogens. So when we're referring to anything having to do with the alpha carbon in terms of NMR, we're referring to the things that are attached to that carbon. As we move out here, though, this is what we're going to call the beta carbon. And as we continue to move out, this is what we call the gamma carbon. And there's delta and epsilon and so on and so forth, okay? Now, if we were to look at the effect on these two, our alpha protons, where we would expect them to show up on the NMR spectrum, again, we would see this drastic effect due to the presence of this electronegative group. So we could find, oh, well, they're going to show up about 3.3 parts per million because of the chlorine, okay? And again, that's the alpha position. Now, when we move to the beta position, again, in the beta position, we have 2 protons, so we can call these guys the beta protons. That electron withdrawing group, that chlorine, still has an effect overall, but it's less than what we find in the alpha position, right? So again, this deshielding effect tapers off with distance. So normally, we would expect to find these guys at about 1.2 parts per million if there were no inductive effects. But because of the presence of that chlorine, that's now 1, 2, 3 sigma bonds away, this still has an overall effect. So when we find these, actually, the signal for these guys is actually 1.6 parts per million. So it is shifted further downfield. There is still some deshielding, but because they're at the beta position, it's much less than what you find at the alpha position. And then as we move out to the gamma position, which is the carbon directly adjacent to that, these guys are all chemically equivalent. They no longer feel the inductive effects or the deshielding effects of this chlorine. So these guys will actually resonate at where you would normally expect them to resonate at, which is 0.9 parts per million. And so overall, the entire purpose of this is saying that the alpha position feels the full effect of that electron withdrawing group, whereas the beta position overall only feels 1/5 of the effect of the alpha position. And that's going to make a little bit more sense in a second. And then when we get out to gamma, gamma is no more effect. Okay, so with that, we can kind of give you guys a few values to keep kind of on, keep in the back of your mind. and allow you to predict with these various values a couple of the various chemical shifts that we could expect depending on the electron withdrawing groups that are present, okay? Okay, so for example, if we dealt, which we're going to deal a lot with just methyl protons, right? So what I mean by methyl protons is these are just going to be the protons that are on a methyl group. So you have a molecule, let's say, kind of like what we just saw. Let's go ahead and redraw this guy. So we have a carbon with a methyl group, with a methyl group, with this, with a hydrogen, to a carbon, with a hydrogen, and a hydrogen, to a methyl group at the end. So if we were looking at a molecule, and we look at this, we find, well, there's no electron withdrawing groups here, right? So these protons and these protons are chemically equivalent with respect to one another, okay? This guy is what we would call methyl protons because, again, they form the end part of that methyl group. So these are what we call methyl protons. We expect methyl protons, absent any electron withdrawing group, to show up at about 0.9 parts per million on the NMR spectrum, right? So that's just always, you can always keep that in mind. If you have a methyl group, you can expect to find the protons at about 0.9 parts per million. We would also expect to find these guys, which are chemically equivalent with respect to one another, but distinct comparatively to these guys. So these are going to be their own signal. We could call these, let's say, HAs. So these guys would give rise to one signal. These guys, we'll call this HB. We would also expect to find HB here at about 0.9 parts per million. Okay, so then if we move into this guy, we have, we'll call this HC. This is what this little group here, this CH2 group, CH2, this is what we call a methylene group, right? And so we would expect to find these guys at about 1.2 parts per million. And you can ask, well, where am I getting these numbers? Literally, I'm telling you these numbers. That's where I'm saying, oh, well, this is a methylene. I can recognize that it's a methylene. I would expect to find those protons resonating at 1.2 parts per million. And then finally, the last one is methane, right? And so a methane group is carbon that's attached to 3 other carbons except for 1 hydrogen, right? So we're talking, this is what we would call a methane hydrogen. We find that right here in this molecule. It's very popular, very common in an isopropyl group. So with this guy, we call this, let's say, HD. Methane hydrogens show up at about 1.7 parts per million, right? So for a molecule like this, which is 1, 2, 3, 4 butane, so 2-methylbutane, we would expect to find 4 different signals, right? 2 of them would show up at 0.9 for the methyl protons. We would have a signal at 1.7, and we would have a signal at 1.2. And I could predict that based on the fact that I have memorized these values. So you should memorize these values. Now, I'm not going to go super in depth into all of the various functional groups and their overall effect on chemical shifts for protons. What I will focus on specifically, though, is the effect that oxygen groups will have on the chemical shifts of various protons. Okay, so oxygen is one of our highly used organic elements, right? So we frequently will have molecules that are some CHO at some point, right? We have a bunch of different functional groups that have oxygen in them, and so you should kind of commit to memory the effect or what we're going to do overall depending on the oxygen functional group that we're dealing with, okay? So for example, let's say that we had a molecule that looked like this, okay? And again, we were trying to predict where these protons in this molecule, so this guy, and then we have 3 out here on the end. We're going to ignore this hydrogen for now. We want to predict where these protons are going to have signals in the NMR spectrum based off of the values that we just memorized, and also based off the fact that this is right next to the oxygen of an alcohol, okay? So note that we'll have 2 signals that are part of this molecule. So these guys are what we'll call HA. And then these guys out here, we can call these guys HB. So these guys are going to give rise to, so this will be a signal, and these three will be a signal. HBs, all of those are chemically equivalent with respect to one another. All of these are chemically equivalent with respect to one another, okay? So the first thing I do is say, okay, well, what type of protons am I dealing with when I talk about HAs? So I look at this and I say, oh, well, this is a CH2 group, right? These are methylene protons. So these are methylene protons, and I can expect to find methylene protons at about 1.2 parts per million because I have committed that to memory, okay? Now, note that these methylene protons are attached to the alpha carbon, the carbon that's directly attached to this electronegative oxygen, this electron withdrawing group that's essentially going to give rise to some sort of deshielding. Now the question is how much, right? How much is the presence of this guy going to affect the chemical shifts of these protons? And so for that, I would go over to this chart, right? So it says specifically the overall effect on alpha protons if I'm dealing with an alcohol or an ether, right? This is the oxygen of an alcohol or an ether. What they tell me to do for alpha protons is add 2.5 parts per million. So normally, without any electron withdrawing groups near these methylene protons, they would have a signal at 1.2. But because they're in the alpha position to the oxygen of an alcohol, we're going to add 2.5 parts per million to them. And so now we would actually really expect them to resonate at 3.7 parts per million. And again, it's shifting the signal of those methylene protons downfield due to the overall inductive effect, due to the deshielding brought about by this oxygen. Okay, so we would expect these guys, HA, to resonate at 3.7 parts per million. What about these HBs over here? So note these HBs are not methylene protons. Instead, they're a CH3 group. They're methyl protons. And so normally we would expect methyl protons to resonate at 0.9 parts per million. But now note, so this was alpha. These guys are at the beta position relative to this oxygen, right? So if they're at the alpha position, then we're going to add 2.5. But if they're at the beta position, we're only going to add 1/5 of that. Because again, that overall deshielding effect tapers off with distance. And what the protons feel at the beta position is about 1/5 of what they would feel at the alpha position. Okay? So instead of adding 2.5, we're going to add 1/5 of 2.5, which ends up being 0.5. So to 0.9, we're going to add 0.5 parts per million. And so we would expect these HB signal to show up around 1.4 parts per million. Okay, so that's what would happen if we were dealing with the oxygen of an alcohol. This is also what would happen if we were dealing with the oxygen of an ether. So remember an ether linkage, if you go back to your functional groups, an ether linkage is a carbon to an oxygen to a carbon. You would also add, for those protons in that alpha position, you would also add 2.5. An ester, if we have an oxygen and an ester looks like this, right? So we're going to circle the functional group. This is the ester. So if we were dealing with protons that were alpha to an ester, it'd be these protons. And an ester is going to have a larger overall effect comparatively to the alcohol or the ether. So to these guys, we would add 3 parts per million, right? As opposed to 2.5. And then the last one that we could possibly see is the carbonyl group, right? So let's say we had something that looked like this. Right, if we were asking, okay, where do we expect to find these protons at, right? These guys, again, that are implied or never drawn in the bond line structure. These guys are also alpha, but they're alpha to a carbonyl. And so for them, we're only going to add 0.1. Not 0.1, 1, sorry, to whatever we'd expect. So normally we'd expect to find these guys at 0.9 because they're methyl protons. Because they're alpha to a carbonyl, we're going to add 1 to that, so we would expect these guys to resonate at 1.9 parts per million. Okay, so this is stuff you should memorize, right? You should know where you'd expect a methyl, a methylene, or a methine proton, and you should know the overall effects of those protons being near the oxygen of an alcohol or an ether, the oxygen of an ester, or the oxygen of a carbonyl group, and what overall effect that's going to have on their chemical shift. Also, whether or not they're in the alpha and beta positions and what that's going to do overall to their chemical shift. Okay, so let's go ahead and try one, or I'm going to do this one and then I'll let you guys try one. So in this molecule, what I want us to do is I want us to predict the chemical shifts for all of the protons that are in the molecule using these values that we've just been given, okay? So first off, we're going to identify all of the signals or all of the chemically non-equivalent protons that we'd expect to find in this molecule, right? And again, the problem with bond line structures is we're looking for hydrogens and there are no hydrogens found, right? So first thing I'm going to do is I'm going to go through and I'm going to go ahead and draw on the hydrogens. So I'm going to start over here. I've got a methyl group at the end, so I know that we have to have 3 hydrogens. I've got a methyl group here, so I also know that we have to have 3 hydrogens. This carbon has only got 3 bonds shown, so I know there's implied hydrogen here. This guy's good, it has 4 bonds shown. This guy here only has 2 bonds shown, so I know that there have to be 2 hydrogen. Same thing here. And then this guy at the end has only 1 bond shown, so there have to be 3 hydrogen. Okay, so those are all the hydrogen. Now we're going to identify which of these guys are chemically equivalent with respect to one another. So first off, all of the hydrogen that are in a methyl group are always chemically equivalent. So these guys are all chemically equivalent, but they are also chemically equivalent with this methyl group as well, right? Because there's free rotation observed around this bond, and so these guys are all going to be chemically equivalent. So we can denote that as, we'll call these guys HAs. So they're all going to give rise to the same signal. Now, as we move in, we have this proton. This proton is distinct and it's different from the HAs. It is not chemically equivalent with anything else, so this would be its own signal. It would be HB. As we move in, these two are equivalent to one another, but they're distinct from everyone else, so this will be their own signal. These guys are HC. We can move in, these guys are chemically equivalent. They're, again, distinct from everyone else, so they'll give rise to their own signal. This is HD. And then at the end, methyl protons are chemically equivalent, but these guys are different than the other methyl protons, so this is HE. And they're all the same with respect to one another. So just as a reminder, methyl protons are almost always chemically equivalent with respect to one another. And then methylene protons, again, these guys, these are frequently chemically equivalent. The only issue you ever have to watch out for is if there's a chirality center. If there's a chirality center, then they are not chemically equivalent. Okay, so we've identified all of the signals, right? So now we're going to predict their chemical shifts. We'll start with HA. So first off, HA specifically is a methyl, or these are methyl protons. So normally we would expect to find them at 0.9 parts per million. Now we're looking for any type of electron withdrawing group. So notice here is my carbonyl. I've got a carbon here. This would be the alpha carbon. And then this guy here, it would be the beta carbon. Same thing, this is another beta carbon. So normally the carbonyl is 0.1 in the alpha position, but because these protons are at the beta position, we're only going to add 1/5 of that 0.1 to it. So this is 1/5 of 1, which is a 0.2. So overall, we would expect this signal at 1.1 parts per million. And so these guys are all the same. Okay, so with that, then we'll move into this guy, our HB. So HB is a methine proton. Normally, we would expect to find that at 1.7. Now, this guy is alpha to a carbonyl, so because of that, it feels the full effect. So we're going to add 1 to it. So we'd expect to find that guy at 2.7 parts per million. We can move to this one, HC. So HC, these guys are methylene protons, so normally they're at 1.2 in the absence of any electron withdrawing groups. But note that this one is not only alpha to a carbonyl, it's also alpha to an ether, right? So the carbonyl is going to add a 1, the ether is going to add a 2.5. And so overall, because of that, we're at 4.7 for those protons. So this is alpha. These guys, HD, they're also alpha to an ether. But now we're not going to feel any more of that carbonyl. We're too far away for it. So these guys, HDs, normally would be at 1.2. We're going to add a 2.5. And so overall, we'd expect to find them at about 3.7. And then finally, we move out to these HEs. We'll go back to black. So these guys, HE, these guys are methyl protons. Normally, we find them at about 0.9. Now, they are beta to an ether. So because of that, we'll add 1/5 of that 2.5. which gives us a 1.4 part per million. So just as a warning, it is helpful to label everything, right? So I gave all of any chemical or any proton that were chemically equivalent, I gave them the same letter, right? So these guys, HAs, are all going to give rise to the same signal that you would expect to find about 1.1. HB, notice I labeled it HB, the HCs, the HDs, the HEs, and specifically where I expect to find them. Okay, so go ahead and try this one on your own. There's 2 of them. Again, we're trying to, number 1, determine how many different protons we have or how many different signals we would expect in the NMR spectrum. And then we're also trying to predict where we would expect to find them in terms of chemical shift in the spectrum. So go ahead and try this one and come back for the answer. Okay, so pretty similar to what we just did. We have very similar structures here. The only thing to note, in that previous problem, we were dealing with a carbonyl, a ketone, and then an ether. But in this problem, they're right next to one another. So this linkage is our ester linkage. And just as a reminder, an ester overall is going to add a 0.3. And then down here, the only real functional group or the only real electron withdrawing group that we need to be aware of here is this carbonyl. And again, we just talked about what a carbonyl does. So this guy is going to add 1.3, or 1, sorry. And again, I'm pointing that up. I'm just saying it's going to add to the alpha position. Don't take that as, oh, this is going to have a signal. It's not going to have a signal. Oxygen does not have any signal in the NMR spectrum, or in the proton NMR, or at all, period. Oxygen does not have a magnetic moment. Okay, so let's go over these. So again, the first part of this is knowing where all the protons are. So we have a methyl group at the end. So all 3 of these protons are going to be one signal. We can call them HA. We've got a methylene group. There is no chirality center in this molecule, so these are going to be chemically equivalent to one another. We'll call them HB. There's no protons here. There's no protons here. We've got 2 methylene protons that are chemically equivalent. They're HC. We've got 2 methylene protons that are chemically equivalent to one another. They're HD. And then finally we get to the methyl at the end, and we've got HE. Okay, so this is our ester linkage. The only thing I will note is that this ester linkage is different on both sides, right? these guys are the thing that's actually going to feel the ester, whereas these things, all they feel is the carbonyl group. So this is actually going to be a 0.1 for the protons that are on the left of this ester linkage, and it's going to be the +3 for the protons that are on the right of the ester linkage. Okay, so I'm going to start at the alpha position. So HB, start up here. HB are those protons. They're methylene, so we'd expect them to be at 1.2. But because they're alpha to a carbonyl, we're going to add 1 to that. So these guys should be at about 2.2. 2.2. We'll move up to the beta position to this carbonyl. So HA, again, normally 0.9. But now they're beta to a carbonyl, so we're going to add in 1/5 of 1. That gives us 1.1. Move over to HC. So HC and HC. So HC, these are methylene protons, normally 1.2, but now they're alpha to the ester. So we're going to add in the 3. We'd expect to find these at 4.2. Move out to HD. HD is at the beta position now. Again, these are methylene protons. So normally 1.2, but now we're going to add to that 1/5 of 3. 1.8. And then finally HE. So HE is at this point in time gamma to that ester. So we've stopped feeling any effect overall. And so because of that, HE are just normally where we would find methyl protons, which is 0.9. This was 4.2. Okay, and so that is where you would expect to predict the chemical shifts of all the protons in this molecule. So I'll go ahead and do the last one. So again, same thing, go through, go ahead and draw in all the protons and determine who's chemically equivalent. So all of these methyl protons are going to give rise to a signal. There's nobody here. We've got 2 protons here. They're going to be their chemically equivalent signal. We have 1 proton here. It's going to be distinct. And then we'll have 6 protons from these 2 methyl groups in the isopropyl group. These guys will all be chemically equivalent with respect to one another. Okay, so HA, we'll start this guy. We're alpha to a carbonyl. For HA, normally it's a methyl group, so it's just 0.9. But now we're alpha to a carbonyl, so I'd expect it instead at 1.9. So 1.9. HB, we're also alpha to a carbonyl. So for HB, normally 1.2. Add in 1. So we expect this at 2.2. Move out to HC. HC is a methane proton. So normally 1.7. It is beta to a carbonyl. So we'll add in 1/5 of the 1, which gives us 1.9. And then finally HD. These guys are gamma to that carbonyl, so you're not going to feel any effect anymore. So for HD, it's just a normal methyl. So just 0.9. There's no additive effects. There's no nearby electron withdrawing groups. Okay, and so that is going to be helpful for the homework. It's also going to be helpful for the exam. It's also very helpful in just knowing when you're actually trying to solve a spectrum, knowing what type of protons you're dealing with and where you're going to expect to find their various chemical shifts. Okay, so we're going to talk about one other thing that's going to affect our chemical shift. And this thing that we're going to talk about is very similar to what we've been dealing with in terms of inductive effects, in terms of deshielding, but kind of the reason for it is similar, but the overall outcome is similar but different. It's hard to kind of explain this. So hopefully I'll be able to illustrate what I mean, right? So when we were talking before about inductive effects and the overall effect that had on our chemical shift values, we are again saying that, okay, we've got our nuclei, right? And so we know that we're going to apply an external magnetic field to our nuclei, right? And again, that nuclei is going to split into one of two possible spin states, the alpha-beta spin state. And the larger the overall field that nuclei feels, the larger the energy spacing between those two spin states, the larger the frequency of energy that nuclei is going to absorb to actually bring that into resonance, right? So that was the whole basis behind NMR spectroscopy. Now, we then talked about, okay, well, we've got electrons in these bonds that are right near our nuclei. And those electrons are also susceptible to magnetic moments, right? They're also susceptible to magnets, right? So because they are charged particles, if we apply an external magnetic field, they're going to begin to circulate, right? And they're going to begin to circulate in a way that's going to create its own little magnetic field, right? And so that magnetic field is very specific in the fact that it will oppose the external magnetic field, right? So these electrons start to circulate. They start to produce their own little magnetic field that opposes that external field, right? And so because of that, our nuclei don't feel as large of a field overall than they would if those electrons weren't there, right? So because of this is kind of reduced in terms of the magnetic field that it actually does feel because of the presence of these circulating electrons, because of the little local field that opposes the overall external magnetic field. So because that magnetic field is reduced, the difference in energy is smaller, and so those nuclei near those electrons are going to absorb energy, are going to absorb radiation at a smaller frequency because of that. Lower frequency, smaller energy difference, that's where we see these lower chemical shifts. Now, again, this process was called shielding. It was those electrons that essentially shielded those nuclei from feeling the full force of that external magnet. Okay, now, when we talked about inductive effects, all that was doing is saying, okay, if we put in some sort of really electronegative group, that's going to remove a lot of that electron density, right, from away from our nuclei. And so because of that, they're going to still circulate, but there's not going to be as many of them. And so they're only going to generate a little bit of a tiny external magnetic field that's going to oppose, a little bit of a tiny magnetic field that's going to oppose the external magnetic field, right? So because of that, they had a larger energy gap because they felt a larger field because a lot of that electron density was withdrawn. They didn't produce as large of a local magnetic field. That process, of course, was called deshielding, right? So electrons shield the nuclei. If we remove them via inductive effects, we deshield them. Now, this last little thing that we're going to talk about is called diamagnetic anisotropy. And the overall reasoning behind it is very, very, very similar, right? So let's imagine that we have something like benzene, right? So benzene, we know, is this aromatic ring, right? We know that benzene has these pi electrons in this compound, right? And these pi electrons we know are delocalized, right? So we can either utilize delocal, that's not even how you spell delocalized, so delocalized throughout the structure, right? We can rationalize that either via resonance structures, or we can look at the molecular orbital diagram and see that the molecular orbital that these electrons lie in are essentially throughout the entirety of the structure and not just localized between any two atoms, okay? All right, so what's going to happen if we take something like benzene and again put it in our NMR machine and apply our external magnetic field is those pi electrons are, just like the normal electrons, going to start to circulate. but they circulate in a very, very, very specific manner, right? So these electrons are going to start to circulate. Because they're circulating, they're also going to be creating their own little magnetic field. But that magnetic field is going to have very specific field lines, or it's going to generate very specific field lines depending on where you're at in the actual compound itself, right? So these guys are going to start to circulate. And so if you were inside the ring, you would find that those magnetic field lines would be opposed to our external magnet. But if you're on the outside of the ring, you find that those field lines are actually enhancing the external magnet or increasing it overall, right? And so we think about benzene, and we think about where these protons that we're going to be seeing in our NMR spectra, those protons are on the outside of the ring, right? And so because of that, these protons that are on the outside of the ring, they're going to feel an overall larger magnetic field because these field lines are essentially enhancing or adding to the overall external magnetic field, right? So it's a similar concept, right? But the rationale behind where we see these signals is slightly different. Here, we're actually adding to the external magnetic field, whereas when we talk about deshielding, we're just removing the impediment that's removing from the external magnetic field, okay? Now again, the overall outcome is the same though. If we feel a larger magnetic field, then we're going to have a larger energy difference, and we're going to absorb light at a higher frequency. So larger magnetic field, larger delta E, higher frequency absorbance, right? And that's going to overall lead to a higher chemical shift. So for example, let's take a molecule like this ethyl benzene here. So note that benzene's kind of weird with respect to chemical equivalency in these protons. We talked about that a little bit. So if we're looking at the chemically equivalent protons in this molecule, we would find that these guys are chemically equivalent. These guys are chemically equivalent. We'll call them B's. And this guy is by itself. We'll call this C. So we'd have three different signals here. But again, because they're protons that are directly attached to this ring, they're going to feel a really large magnetic field, and so we're going to expect them at a really high chemical shift. And so overall, what we find here for these guys is them giving rise to a signal at about 7 to 8 part per million, right? And so know that this signal is really ugly, and the reason why it's so ugly is because essentially you do have three different protons overlapping and giving rise to this. This is what we would call a multiplet. And I'll talk about, because a lot of times you're not going to get a multiplet. You'll get something that looks nice and pretty like this. This is what we call a quartet, where you actually see there's 4 distinct peaks. Or here, this is what we call a triplet, where you actually see there are 3 distinct peaks. This is not a quartet or a triplet or anything like that. This is a multiplet. It's 3 different signals that are overlying, but just note that their overall chemical shift is really, really, really high due to this diamagnetic anisotropy, okay? So this word anisotropy, all that's referring to is the fact that you feel the magnetic field differently depending on the region the molecule you're at. If we were inside of the ring, we would actually feel less of a field. It'd be very much like the shielding effect overall, comparatively to if we're on the outside of the ring where we feel more, right? Those differences are what are giving rise to this word anisotropy. Okay, so it's not even due to things that are directly attached to pi electrons. We'll also see a similar effect to these hydrogens that are nearby the overall aromatic ring. So these guys will also be shifted. So again, normally these guys are methylene protons. We'd expect to find them at 1.2, but the actual signal for them is here at about 2.5. So they're being shifted because of their nearby presence with this guy. And then even these little methyl protons are being slightly affected by it. We would normally find them about 0.9, and these guys are a little bit above 1 over here. This is the overall signal for them, right? Now, we're not going to do necessarily a similar thing to what we did with the inductive effects, because it's a little bit harder to predict. But what I will say is that I will give you the majority of these predictable chemical shifts due to this diamagnetic anisotropy, right? So I showed you like the protons on the aromatic ring and how far downfield those guys showed up, how high of a chemical shift they had. We're going to find that effect overall for any compound or any proton that's near any type of pi electrons, right? So this includes just double bonds as well as triple bonds. So for example, we've already gone over where we'd expect to find methyl, methylene, and methane. For an allylic proton, so remember that there are two different positions. We have a double bond here. We have a vinylic position and we have an allylic position. The vinylic position is the position that is like essentially the carbon that makes up the double bond, whereas the allylic is the position directly adjacent to that. So this is allylic, right? So an allylic proton, because of its presence nearby to these pi electrons, again, is going to be shifted slightly downfield, and so we'd expect to find that about 2. Same thing for protons that are directly attached to a triple bond. So an alkynyl proton ends up being about 2.5. If you're an aromatic ethyl or a methyl group, you could expect to find those about 2.5. So again, this is very similar to what we saw with the ethyl benzene, right? If we have a benzene ring and then we have hydrogens that are directly attached to that carbon that are off that, those are going to be shifted as well. We would expect that to be, again, about 2.5. And then vinylic is about 4.5 to 6.5. Again, it's going to depend. Those aryl protons, which is what we saw with the benzene ring and stuff, the protons on the benzene ring. Again, we're going to usually expect a multiplet at about 6.5 to 8. And then there are 3 others that are going to be really helpful and informative here. So the proton that's attached to the oxygen of an alcohol, we're going to find that about 2 to 5 depending. And usually there's going to be a very distinct signature for this guy compared to everyone else that we'll talk about when we talk about multiplicity. But just note, for an alcohol, we'd expect it to be about 2 to 5. The proton that is from an aldehyde is at about 10. So these are really, really, really far downfield. And then the proton of a carboxylic acid ends up at about 12, right? So things that I won't tell you would be this guy, this guy, this guy. I won't talk about the additive or the inductive effects. You should be able to know that. But things like this, I would have to give this to you. I don't expect you guys to memorize this. But you should be aware of a couple of these various functional groups. So the alcohol, for example, the aldehyde proton, the carboxylic acid protons, and where you'd expect to find them in terms of chemical shift. Okay, so let's go ahead and try these guys. So the only thing I wanted to note about the diamagnetic anisotropy is that that is not something that we're going to add on to things, right? The only time we do that is with those inductive groups, is with the nearby presence of an oxygen of an alcohol, the oxygen of an ether, etc. If we have like a double bond here, I'm not going to say, oh, I'm going to add whatever to these protons to make up for that. That's not going to happen. But go ahead. We've got 2 different molecules here. I want you to predict the chemical shifts of all of the protons in the molecules. So give that a try and then come back for the answer. Okay, so we'll go ahead and start with this guy on the left. So again, my first step in doing this is identifying all of my protons. So I've got 3 methyl protons out here. They're all going to be chemically equivalent with respect to one another, so I'll call them HAs. I'm going to move to the double bond here. So this carbon has no protons, but then up here, we do have 2 protons that are not being drawn. So we have a proton here and a proton here. One big thing to note here is that this is a double bond, right? And there's not free rotation allowed around a double bond. Chemically equivalent protons have the same electronic environment. Because there's not free rotation about this double bond, these guys have different electronic environments, so these guys are not chemically equivalent, right? So one of them will give rise to one signal, and one of them will give rise to another. As we move down, we've got methylene protons here. They are chemically equivalent. There is no chirality center in this molecule, so we'll call these HDs. We've got another set of methylene protons. They are distinct from the Ds, but they are chemically equivalent with respect to one another. We'll call them HE. And then finally, one that we've been ignoring entirely is this proton on the alcohol of the hydroxyl group, and we'll call this HF. A, B, C, D, E, F. Okay, so we're going to utilize those values that I gave you in the previous table. So I'm going to go ahead and start with HC and HB. So these guys are what we would call vanillic protons, right? And so vanillic protons, let me just highlight these. So this guy and this guy, these are vanillic protons. So HC and HB. And in that table, it tells us the vanillic protons show up at about 4.5 to 6.5. Again, there's not much, we can't do any better than that, right? So if I said, hey, where do you expect to find these two protons in terms of their chemical shifts, that's the range that you would have to give me, because there's not much else I can do about that. If we move out to HA, HAs are methyl protons, but note that this methyl proton, these guys are not in the vanillic position, but they're in the allylic position, right? And so according to that table, allylic protons show up at about 2. So HAs, we would expect to find at about 2 parts per million. Same thing for these guys. These guys are allylic as well, but they're going to be shifted a little bit more because, again, these are not only they're allylic, but they're also beta to an oxygen and alcohol group. So normally we would find these at about 2, but now we're going to add in that beta, that 1/5 of that 2.5. Which gives us an approximately 2.5 parts per million for these HDs. And again, this is an approximate 2.5. Now that we've moved out to HE, we're no longer feeling the diamagnetic anisotropy effect, right? We're no longer feeling the pi electrons in this double bond, but we are now feeling the inductive effects of the alcohol group. So we're alpha to the alcohol at this point in time. Again, HE would normally be at 1.2. But because we're alpha to the alcohol, we're going to add 2.5 to that. And so we would expect to find these guys at about 3.7. And then finally, HF. HF, we would have to reference that chart. It's the hydrogen that's attached to the hydroxyl of an alcohol. And again, this gave us a range. It's about 2 to 5 parts per million. Okay, so let's move over to this guy. Again, I'm going to identify all the protons first. So I've got an H, an H, an H. These guys are all equivalent. Got an oxygen, got a carbon that's already got 4 bonds to it. We've got an H, an H, an H. Got an H, an H, an H. 4 bonds already, and then we've got an H on the end, right? So this is HA. These guys are HBs. These guys are HBs again. They're chemically equivalent. Damn it. And this guy will be HC. Okay, so we've got kind of a mixture here between the diamagnetic, anisotropy effects, and inductive effects. So first off, we'll start with HA. HA is, here we have an oxygen, so this is an ether. HAs are alpha to an ether. So again, normally we'd find them at 0.9, but because they're alpha to an ether, we're going to add 2.5. So that gives us 3.4. So that's where we expect to find them. For HB, we're not in an allylic position. These guys would be alpha. These guys are then beta to that ether. So again, for HB, normally we'd find the 0.9, but now because we're beta to that ether, we're only going to get 1/5 of that ether effect, which gives us about 1.4. And then for HC, again, this isn't an inductive effect. It's the diamagnetic anisotropy effect. It's the effect of those pi electrons. And this is the one that you would have to look in the table for. So we'll find that this is what is called an alkynyl proton. And we would expect to find that, according to the table, about 2.5 parts per million. Okay, so hopefully you guys did okay on those. And the difference between the inductive effects and the pi electrons, the diamagnetic anisotropy effect, hopefully that is clear, and when to use one versus when to use the other. Okay, so we just essentially finished off talking about chemical shift, right, which is one of the first bits of information that a signal in an NMR spectrum is going to give us, right? Now it's going to give us the at least the knowledge of whether or not an electron withdrawing group is nearby. It's going to give us how many actual chemically non-equivalent protons there are, etc. The second bit of information that we can take away from a chemical signal or a signal in the NMR spectrum is something that's called integration, right? So if you guys have taken integral calculus, you know that if you have a curve, let's say, and you integrate under the curve, that generally will give you the number of things that are giving rise to that signal under the curve. It's the exact same thing with respect to NMR spectroscopy, right? So if we take each signal that we have and we integrate under each peak, the integral value will actually give us the number of protons in a relative amount that's giving rise to that peak, right? And I specify that as being a relative amount. It's not giving us the actual number, because that would be a gigantic amount, but it's giving us the relative number of protons that are giving rise to each peak, right? So sometimes this can be nice and easy. Sometimes it'll actually be written for you on the spectrum where it says, oh, this integrates to 1, this integrates to 3, to 4, to 2, etc. Sometimes it's not like that, though. So sometimes instead they'll actually give you the integral values, and you'll have to utilize that data to figure out the numbers of protons that are actually giving rise to each peak. So for example, in this spectrum, they actually give us the integration values, and those end up being 27 for this signal, 40.2 for this signal, 28.4 for this signal, and then 42.2 for this signal. And so part of what you'll have to do is take these and actually make them useful. And so to do that, what we're going to do is we're going to go ahead and determine the smallest number in terms of these integration values, and we're going to divide all of the numbers by that. We're going to essentially reduce down to the smallest value. So the smallest value for these guys is 27. So we're going to divide every number here by 27. And what we end up with is 27 divided by 27 is a 1. This 40.2 divided by 27 is 1.48. This 28.4 divided by 27 is a 1.05. And then this 42.2 divided by 27 is a 1.56. Now, ideally, when you do this, you'll get some sort of nice whole number values, like 1 and 2 and 3. But in this case, we didn't, right? We got a 1, we got a 1, we got a 1.48, we got a 1, and we got a 1.56, right? So we can round to nearest whole number values. So this one, I would say to integrate it to 1. This one would also integrate to 1. We can go ahead and round that down. But this 1.48 and this 1.56, those are not integral values, right? So they are going to have to stay at that 1.5 and that 1.5. Now, again, the reason why we're getting 1.5 is because this is giving us the relative number and not the absolute number. If we wanted to get rid of that 1.5, then we can, but we need to multiply everything by a particular number. So if I took all of these guys and I multiplied by 2, that would give me a value of 2, giving rise to this guy, 3, a 2, and a 3. And those would be not the absolute value necessarily, but at least the whole number integral value of protons that are giving rise to each signal. Now, just as a note, you'd say, well, what type of group on a molecule would be giving rise to or have an integral value of 3 protons? Well, that usually ends up being something like a nice methyl group by itself, right? What about 2 protons? Oh, that ends up being usually a nice methylene group by itself, right? Okay, so again, just as a buyer beware, or just one little note here, regardless, these integral values are going to be giving you is the relative number. It's not going to be the absolute number, as I've mentioned. So usually you'll need to couple these with the molecular formula of the compound to know the actual number of proton giving rise to each signal. So for example, in this molecule, we have 3 protons that are going to give rise to one signal, and then all of these 9 protons that are going to give rise to another signal, right? So when we do the integral for this type of compound, we're not going to see a 3:9 ratio. What instead we're going to see is a 1:3 ratio, right? The way we're going to take that and figure out that it's a 3:9 ratio is going to be taking this and coupling with the fact that the molecular formula here is 1, 2, 3, 4, 5, C5H12O. And so a 1:3 ratio doesn't make sense if there are 12 protons, right? A 3:9 ratio is what makes sense if there are 12 protons. Okay, so again, sometimes those integrals will be done for you, so they'll literally be written, oh, this is 1 proton, this is 2 proton, 3, or sometimes you'll actually have to do them yourselves by, again, dividing by the smallest integration value and then multiplying by whatever number you need to get everyone to whole number values.